So I want to look at some examples of the structure factor. So in the previous lecture we derived the structure factor. The structure factor corresponding to plane HKL is given by the product of two structure factors, one corresponding to the lattice and one corresponding to the basis. So if you recall, there is a structure factor Fa e raised to power minus I 2 pi Ra GHKL. This term is taken over all atoms A inside the basis. And you multiply this with a structure factor corresponding to the lattice sites minus I 2 pi Rn GHKL, where n is now taken over the points inside the lattice. Okay, the lattice points. For primitive, there's just one term in here. For body center, there are two terms. For face center, there are 4 terms. And for any base center, there are 2 terms. Now, this gives us the overall structure factor. This term Fa corresponds to a single atom. It's called the atomic scattering factor. And it can be computed, and we'll compute this today as well. So let's look at a few examples. First of all, let's take a very simple example of a primitive lattice. Let's say cesium chloride, which is primitive cubic. So this term here, this term is, what is this term? SHKL for the lattice. So where is that point? That point is just on the edge. So R is 0, 0, 0. GHKL is H A star plus K B star plus C star. You take the dot product, multiplying 0 with anything, this becomes 0. So this just becomes 1. So this is 1 for any primitive lattice. And now let's look at the basis. Now the basis, what is the basis? It's a cesium atom and a chloride atom. So what is a basis? We've looked at the structure of cesium chloride already. Cubic, cesium, and chlorine at the center of the body of this cell, but it's not a body-centered cubic, it's primitive. So what are the coordinates for cesium and chloride? Cesium ion, chloride ion?
0, 0, 0 and 5.
So these are the RAs. Corresponding to cesium will have an F structure, atomic scattering factor for cesium, and for chlorine will have FCl. So the SHKL for the basis becomes FCS. This is, you put in zeros, you get 1 plus F chloride E minus I pi H plus K plus L. Okay, so this is the overall structure factor, and this is going to tell us the intensity of the diffraction peaks. First of all, are there any absences, which means are there certain values of H, K and L for which this term becomes 0? None. So all H, K, L, all kinds of reflections are allowed. There are no conditions for the reflection. So if you look at the group tables, at the extreme right you have reflection conditions. For primitive cesium chloride, for primitive cells, you look at the Wyckoff positions which correspond to cesium and chloride, and you will find out there are no reflection conditions. All kinds of planes can reflect. It of course depends upon the wavelength, but this is our basis. This is our structure factor, and it's a total structure factor because then you multiply this with 1, you get the total structure factor. So S turns out to be, overall S turns out to be FCS plus FCL when HKL is an even number, some even number, correct? And it's FCS minus FCL when this is an odd number, correct? So when you look at the diffraction intensities, now this is structure factor. The intensities will then be given by, will be proportional to the square of S bar square. So you'll get two kinds of intensities. One will have intensities FCS plus FCL squared, the other will have FCS minus FCL squared. By the way, these F's will also be dependent on the angle, as I'll show in a minute. Okay, but nevertheless, now all peaks in the diffraction pattern do not have the same intensity. Okay, any questions about this? Now, if you look at our second example, so S for the lattice is 1 plus E minus I pi H plus K plus L. This is the HKL, the structure factor for the body centered. Okay? Its reciprocal lattice is face centered, but the lattice itself is body centered. Now this thing is only non-zero when H plus K plus L is even. Otherwise it's 0. So for a body centered lattice, the structure factor vanishes unless H plus K plus L is even. Right? So if this sum is even, then this factor becomes 2. And if this sum is odd, this factor becomes 0. So H plus K plus L equals 2n is the condition for this structure factor to be non-zero and for a diffraction peak to exist. So only those reflections exist for which H plus K plus L is even. That's the characteristic of a body centered lattice. And it's 0 when H plus K plus L is not even. Okay. So whenever you have a body centered lattice and a crystal structure that crystallizes in the body centered cubic Bravais lattice, only those peaks exist for which HK plus L is even. Okay. So now let's look at the basis. So what's the basis for iron, BCC iron? It's just a single atom. So this is going to be 1. That atom can be taken to be at 0, 0, 0. So overall structure factor is simply arising from the lattice. And there is a systematic absence when H plus K plus L is odd. So only these reflections exist, 0, 0, 0 from this plane, 1 1 0. 1 1 1 will not exist. There will be no reflection from the 1 1 1 plane. That will be systematically absent from the diffraction pattern. 2 0 0, 2 2 0, 2 1 1 will exist, etc. And of course, the entire family of equivalent planes which are equivalent to these planes will cast reflections. For example, 0 0 0 is no plane. So for example, this would like to write the entire family of planes like this. This will have 1 1 0, 1 1 bar 0, 1 bar 1 0, 1 bar 1 bar 0, etc. Okay. And technically, since the structure factors are all the same, all the non-zero structure factors are the same, technically they should be of the same intensity. However, the F itself, the S basis is F of iron. This factor itself can depend upon theta. So if you look at all the peaks, there will be some theta dependence, as we're going to show in a minute. Okay, now I would like you to look at one structure, and that is our third example from, say, let's look at sodium chloride. Now, sodium chloride crystallizes in the FCC structure. This is the unit cell for FCC. Now, if I were to look at the S lattice for this F structure, FCC structure, it's going to be 1 plus E minus I pi 2 pi over 2 with 2 terms. So I get minus I pi H plus K H plus L all right. Now I can find out when will this structure factor for the lattice be non-zero. So for 0 0 0, these are HKL values. This is going to be 4. For 1 0 0, this is going to be 0. For 1 1 0, this is again going to be 0. For 1 1 1, let's see what do we get. 1 plus H plus K is 2, 1 plus 1 plus 1, I'll get 4, correct? I get 4 all the time. Now, these indices are unmixed, they're all odd. So I get a non-zero value. Non-zero value. Here I have mixed, even and odd are mixed, so I get 0. 2 0 0 will give me 4. 2 1 0 will give me 0, etc. So only unmixed indices will give reflections, and systematically absent will be those reflections which come from planes that have mixed indices. Now let's look at the F, the structure factor for the basis. Now there's a sodium and there's a chlorine. In fact, there are ions, sodium ion and a chloride ion in the structure. So what are the coordinates, atomic coordinates for these ions? So if I draw the structure here, So if my sodiums are on the vertices, these sodium ions must also be at the centers of the faces, right? Okay, so these are all the sodium ions. And chloride ions are halfway in between. So there's a chloride ion here, chloride ion here, here, here. Okay, so these are here, 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 here. So I hope you're following the web page that I'm uploading. I've kind of given you some remarks on. I would request you to download the software Vesta and try plotting these and visualizing these structures. Vesta is in fact a very popular software. It can help you put all the atoms. It can help you visualize this. It can rotate this object so you can look at it from different orientations. You can slice it. You can extend the unit cell so you can look at a larger volume. You could also look at certain planes. You could also look at polyhedra. So you can see, you make this the center, the chloride ion at the center, and see which other iron is it coordinated with. So you can identify bonds, find distances between atoms and so on. And you can also simulate the diffraction pattern. And then you can load lots of crystal structures from this, an open crystallography database, which has lots and lots of structures. And they produce these CIF files, the crystallographic information files, and there are tens of thousands of them are available. You can load them directly into Vesta. So the huge database available. So this is sodium chloride. So what are the coordinates for sodium? So what is the basis for sodium? So, okay, can anyone speak up?
0, 0.
Sodium का value बताओ.
Sorry. 0, 0.
And chloride?
And chloride का हम half 0, 0 कर सकते हैं.
Half 0, 0, okay. So this is the basis, that's it. Sorry? लेकिन वो we've already identified a lattice. The lattice is face centered. So you put this basis on each of those, on each of the 4 lattice points. Each of these 4 lattice points, you put this basis on these lattice points. So this structure you put here, so you get a sodium here and a chloride here. You put here, you get a sodium here and a chloride here. You put here, you get a sodium here and a chloride here. So you put this basis, this pair of atoms on each lattice point. You generate the entire structure. This is convolution. Now for this S basis, I would have F sodium, which is the atomic scattering factor, which comes from atomic physics. For sodium, E minus I pi etc. This gets you 1 plus FCl E minus I pi, and then you have H. Correct? So because this location is half A. So this is the S basis, and then you have the S lattice. Now what you would like to do is you find an overall structure factor, which will be 1 plus E minus I pi H plus K plus minus I pi H plus L plus E minus I pi K plus L and you multiply this with FNA plus FCLE minus I pi H. Okay. So if I would to complete this table a little bit, I just want to erase this part here. If I look at this entry, so this is 4 over here, and here I get H is 0, so I get F and A plus FCLB multiplied by 4. This entry, I don't need to worry about these entries because these are zeros anyway. So this entry will be, H is now 1, FNA minus FCL. Let's look at this entry. H is now 2, FNA plus FCL. Let's look at one more entry. Let's look at 2, 2, 0. Once again I get FNA plus FCL. And now take the modulus square. This will become FNA plus FACL square, modulus square. This will become FNA minus F. So the peaks will distribute into two kinds of heights. One with large heights and the other will have short heights. And only those reflections will exist for which the HKL values are unmixed. So let me give you some examples. So in our laboratory we took some data for sodium chloride and some other substances, and let's see what that data looks like. Off from sample, and what you're measuring is the intensity of X-ray detections versus theta, the scattering angle, and generally you plot versus 2 theta, because 2 theta is the diversion angle. So if you look at sodium chloride, the peaks here are of two kinds. One are these large peaks, and the other are these very small peaks. One corresponding to FNA plus FACL and other to FNA minus FCL squared. These intensities are not the same because as theta goes up, the atomic scattering factor goes down. The F goes down. So now you have X-rays coming in. Most of those X-rays are scattered in the forward direction because destructive interference is less likely to happen in the forward direction. Okay. For angles bigger than 0, as the angle goes up at a certain angle, there is a higher propensity for destructive interference from the scattering waves. So the scattering factor drops, and we can derive this as well. But there are other factors which contribute to the dependence of the intensity on angle. There could be polarization effects, there could be thermal effects which give rise to broadening of the peaks, there could be strain inside the system, there could be other effects such as the Compton effect also happening, there could be secondary absorptions and reflections that are taking place. So it's a very complicated process. So this is sodium chloride, and then what happens is that you kind of take this spectrum and then you would like to match it. You have a trial solution, you have a trial spectrum, and then you look at whether your experiment matches that prediction. And if it does, you can refine it further using precise algorithms. So what you do in these cases is that this is the ideal spectrum for sodium chloride. And if you look at this ideal spectrum, here is the ideal spectrum. You look at these peaks. These are just stem, it's a stem function. It's just showing the heights of certain stems. There is a reflection corresponding to 1, 1, 1, 2, 0, 0, unmixed, all unmixed. So if you take an ideal NaCl structure and simulate it, this is what the pattern looks like, and this is what we observe. Okay. So the observation and the predictions match. Look at these very small peaks here. This is a small peak corresponding to 400. So what you really want to do is, when you get this spectrum, you index the peaks. You tell which plane does each peak correspond to. When you index the peaks and you know their angles, so this is your 2 theta, you make a table like the one we made in our previous class, and then from that table, you know it's cubic, you find out the lattice parameters. Okay. From the systematic absences, you can tell that this is a face-centered Bravais lattice. Yes, please.
So what's specifically happening at 2 theta is equal to, I guess, 32, 33 degrees?
ये वाला इधर.
ये जो सबसे high peak है.
So this is coming from FNA plus FCL modulus squared. So there is a reflection due to 200. ठीक है, हमने टेबल में भी देखा था पीछे. ये वो पीक है. This is iron. And here you see that only those peaks exist for which the sum of the HKL indices is even, and there is a dependence of the intensity on the theta. Here is zinc oxide, which is hexagonal. You can have a very large number of peaks, predicted peaks like this, and then your spectrum is matched with this prediction, and then you can have figures of merit of how good the match is and so on. And then you index all of these peaks. You can tell which plane is each peak coming from. Okay, and from there, from computer algorithms and systematic processes, you can then find out the size of the unit cell. You've already determined the shape of the unit cell, and now you can find out the size as well. What are A, B, C, and what are the angles alpha, beta, gamma. So this is lead oxide. This is lithium carbonate, monoclinic. Okay, so all of these spectra were taken in the laboratory downstairs. Okay, so it's a beautiful, it's a fascinating field. And you can spend lifetimes and lifetimes on this. Now copper oxide, when I gave the sample of copper oxide to Dr. Mehdi, this is what the spectrum looks like. It doesn't match. There are two different kinds of coppers depending upon the oxidation state of copper. The oxidation state of copper could be +2 or +4, and it matched neither copper oxide nor neither cuprous oxide nor cupric oxide. But then it was found out to be a mixture of the two, and you can find out the relative fractions of mixture. So this is a very valuable technique for diagnostics as well. Okay, so this is how you generally do the analysis. So the one thing now I would like to mention is a little bit about the dependence of the atomic scattering factor on the angle, an electron. And X-rays are coming in and they are scattered. The Bragg formalism describes the X-ray diffraction process as reflection from planes, which is totally equivalent to the actual thing that is happening, which is scattering from electron. So now if I have an electron and it scatters radiation, suppose this vector from this point is d. and you have a detector here. This is our detector. And the wave vector of X-rays that is coming out is k. Then the signal, the X-ray detection intensity, or the field, the electromagnetic field that will be detected here, is going to be proportional to some amplitude of the incident radiation, and it will have some phase as well, because electromagnetic waves have a phase, and that's how the diffraction is occurring. Certain phases are there which let certain directions to allow for destructive interference, so that scattering only happens at certain angles. So there has to be a phase, and that phase of course is EI, this K and a D. Okay. Huh? K wave vector, X-ray ka wave vector, 2 pi over lambda. Now this is, now when this electron absorbs radiation, it scatters, and it's a point source. So this scattering, the wave fronts for the scattered X-rays are really spherical. From a point source, the radiation has to be spherical. So for spherical wave fronts, optics tells, or electromagnetic wave theory tells you that you need to divide by d as well to keep the energy constant, because you go for bigger values of d's, the area goes up as d square. So the intensity has to go down by 1 over d square, so to keep the overall energy constant. So this is the kind of scattering amplitude that is received over here. And there is some intrinsic factor due to the electron. Let's call it Fe. Now this is due to one electron. Now suppose there are two electrons. There is an electron over here, an electron over here, and these electrons are separated by distance r. And now you have a detector which is placed far apart. These electrons are very small, so this inter-electron distance is much smaller than this d. This vector of course will be d minus r, and d minus r will roughly be the same as d, because this r is small, and you have, in the same manner, you have X-rays coming in. Now there's a phase associated with this scattered wave and a phase associated with this scattered wave, and those phases will let those scattered waves to interfere. Correct? Now if you now find out the scattered intensity from these two electrons, it's going to be Fe A, and then you have from this first electron Ei Kd over d. From the second electron you have Ei K, now d minus r from the second electron over d minus r. Now d minus r is roughly the same as d. So you can put. So overall you will get a u from two electrons is Fe A over d. I take this as common, Ei Kd 1 plus E minus I K dotted with R. So any electron which is at a position vector with respect to some origin R will give a contribution to the phase, will add to a phase by E raised to minus I K dot R. So now you have, if you have a distribution of electrons as you have in an atom. Now let's consider an atom which has a continuous distribution of electrons. An electron, say in an atom, we know what the wave function of an electron cloud is inside an atom. That wave function has a certain probability density, rho r. This is the modulus square of the wave function of the electron. Now an electron at a position r with respect to some origin, which could be the nucleus of the atom, will give rise to a phase E minus I K dotted with R. Correct? And then what you would like to do is you would like to integrate this to find out the overall scattered amplitude at a distance for a detector which is far away from an atom. So now you have an electron cloud instead. This is your electron cloud. This is the probability density of electrons inside an atom. Could be an s orbital, a p orbital, or anything. In a big atom, you have some distribution of electrons. And you've already studied quantum physics to that extent. And now you are shining this with X-rays are coming in, and you have a detector far apart. And this is measuring the amplitude of the scattered waves from this electron clouds inside the atom. Okay, so this is your overall. You can multiply this with Fe, any other factors that you like. A, capital D is a geometrical factor. And this will give you some semblance of the atomic scattering factor Fa. Okay, in fact, K, this can be simplified even further. Students, तो नहीं आगे बार बस 2-3 मिनट का काम रह गया. This is my nucleus here. And the electrons, this is the electron cloud. And assume it's a spherically symmetric electron cloud. Now X-rays are coming in, hitting this atom. And the nucleus is the origin of my coordinate frame. X-rays are coming in, and these X-rays have a unit vector S naught, which identifies the direction of the incoming waves. And what we want to look at is the scattered direction. S is another unit vector in the direction of the scattered wave. Okay. Now we do know that if I were to extend this S naught here, okay, this is my S naught, then this vector here, this vector that I've drawn here, this one, is S minus S naught. Okay, and this angle is 2 theta, correct? Therefore, this angle is theta. Now, these are unit vectors. These are unit vectors. So, in order to get a k vector from a unit vector, I need to multiply this with the momentum of the X-ray, which is 2 pi over lambda. So, if I multiply this thing 2 pi over lambda with S minus S naught, I will get my k, which is the direction of the scattered radiation, or the deviation in which my radiation is scattered, k. Now, but I know that S minus S naught from this geometry, this is theta, so this is of course sine theta. It's a unit vector S naught, so this is sine theta. So this is 2 sine theta. Therefore, this integral, if I would like to kind of solve this integral, it's a 3-dimensional integral over volume. If I would like to solve this integral, I could replace this k with 4 pi over lambda sine theta. And I need to also know what kind of electron I'm talking about. Suppose I'm looking at an electron over here, which has a position vector r. So this is the position vector of the electron from where you're looking at the scattered wave. So if I draw another axis here, call this another angle phi. If I assume spherical symmetry, then this phi extends from 0 to pi inside the atom. And my k vector, which is the direction of this vector, is my k vector. This vector k points, of course, in this direction, k. Okay, so this is the direction of k, which is s minus s naught. And the angle between r and k is phi. So this helps me solve this integral. How? Fe over a divided by d. Let's keep this as d cube over r for the time being, rho r exponent minus I, k is 4 pi over lambda sine theta, and the angle between k and r is cos phi. So what this means is that my Fa can now be computed as Fe a over d. Now let's break out d cube r. It's a volume integral. So it goes from r goes from some value 0 to probably infinity, but let's say that the atom has a finite size, some maximum r exists. This is dr. Now the azimuthal coordinates is what is generally called the phi coordinate is over all the 2 pi angle. So I don't need to integrate, I just multiply this with 2 pi. I need to consider this polar angle, which in this diagram I've called phi. So that will give me phi goes from 0 to pi, and I need to integrate over phi, but the volume integral has this metric r square sine of phi. This comes from volume integration. And then I have this rho r. Now rho r, instead of the vector I just write r because it's a spherically symmetric problem. And then I have e raised to power minus I 4 pi over lambda sine theta cos phi. Correct? I can bring this. So far so good. So this factor 4 pi over lambda sine phi, I call it mu, some mu. Okay? Sorry? Sine theta cos phi है ना? Sorry? वही लिखा होगा. I call this variable mu. This fact, there is no theta elsewhere, there is no integration over theta. So this will depend upon theta. So this becomes 2 pi Fe a over d dr r square rho r d phi e minus mu cos phi and sine phi. Okay? So I need to integrate this, and that I can easily do by substitution. I put cosine phi is mu, then d mu is minus sine phi d phi. So this becomes from pi to 0 d mu e minus I mu u. यार u इतना अच्छा लफ्ज़ नहीं यहाँ पे. Let's call it z. Okay, this will be a sinc function. The integral of this will be a sinc function. It will go down with, if I plot this, so this integral is sine mu r over mu r. If I calculate this, this will be, I think, of this kind. It's going to go down with mu, where mu is the angle. So for large thetas, this factor goes down. And I can put in explicit values of the probability density function. For example, for an s orbital, what is rho for an s orbital? Is proportional to e raised to power minus r over some factor which resembles the Bohr constant. So I can put this value in here and compute this for different kinds of electron distributions. This will give me the theta dependence of this atomic scattering factor. Generally, there are tables available that plot f a versus mu or sine theta, and generally these tables and graphs look like this. For large thetas, these FAs go down, and for theta equals 0, if you put theta equals 0 here, this thing becomes 1, this becomes independent of theta, and you're left with this integral. Now what is purely, what is this integral equal to? If this is 1, for theta equals 0 degrees, this entire thing becomes 1. So what is this thing equal to? This is charge density. Total charge, which is called the atomic number. So if I take aluminium at theta equals 0, this will have some, it will start off from, say, the atomic number of aluminium, 13. Magnesium, this will start from 12. Magnesium will have a curve like this. Carbon may have a curve like this. So they all start off from the atomic numbers. But there are additional factors that control the dependence of the intensities on theta, like polarization, thermal effects, other instrumental aberrations. But this is a broad sense which tells us that even though the structure factor calculation tells us what the intensities are going to be broadly, there's an additional modulation due to the dependence of the atomic scattering factors on the angle theta. Now this finishes our discussion on diffraction theory, on the structure of crystals. In the next lecture, what we're going to look at is if there are certain kinds of waves inside the crystal, like electron waves, and they see this periodic structure, what kind of effects do we see? What kind of implications does that have for the dynamics of the crystal, for conductivity, and so on?
वो ज़्यादा quantum mechanics based है.
हाँ. तो आपको उनमें से बहुत पसंद है? Familiar, but this is really important. If you want to study materials, 3/4 of all the physicists who work in laboratories work with condensed matter systems. So you really need to understand what materials, how do materials form. All right.